For decades, physicists have struggled with one deceptively simple question: how do complex surfaces grow over time? Whether it is crystals forming atom by atom, bacterial colonies spreading across a surface, flames advancing through combustible material, or even certain patterns emerging in artificial intelligence systems, growth processes often appear chaotic and unpredictable. Yet in 1986, physicists Kardar, Giorgio Parisi, and Zhang proposed a remarkable idea. They suggested that many completely different systems might secretly obey the same universal mathematical law. Their theory, now known as the Kardar-Parisi-Zhang or KPZ equation, became one of the most influential concepts in statistical physics. For nearly 40 years, however, one major challenge remained unresolved: proving experimentally that this universal growth behavior truly exists in 2 dimensions. Now, researchers at the University of Würzburg have finally achieved that breakthrough. The discovery represents a major milestone in modern physics because the KPZ framework is not just about one specific material or phenomenon. It is about universality, the idea that systems governed by randomness and nonlinear interactions can still evolve according to hidden mathematical rules. In practice, growth is incredibly difficult to predict because real systems are constantly fluctuating. Surfaces do not expand smoothly. They develop irregular structures, sudden instabilities, and random variations. Tiny disturbances amplify over time, producing complex patterns that are notoriously hard to model. This becomes even more difficult when the system exists far from equilibrium, meaning energy is constantly flowing through it rather than remaining stable and balanced. To investigate this problem, the Würzburg researchers engineered an extraordinarily delicate quantum experiment capable of tracking growth both in space and time simultaneously. They used a semiconductor made from gallium arsenide and cooled it to temperatures just a few degrees above absolute zero, approximately minus 269 degrees Celsius. Under these ultra-cold conditions, they illuminated the material continuously with a laser. This generated exotic quantum particles known as Polaritons, unusual hybrids formed when light particles called photons strongly interact with excitons, which are electron hole pairs inside the semiconductor. These Polaritons are neither pure matter nor pure light. Instead, they behave as a combined quantum entity with properties of both. What makes Polaritons especially valuable for studying growth dynamics is their extremely short lifetime. They exist only for a few trillionths of a second before decaying back into light. Yet during that brief existence, they form a rapidly evolving quantum system that can be precisely measured. By tracking how these Polaritons spread, fluctuate, and interact across the semiconductor surface, the researchers were able to observe the statistical behavior of a growing system in unprecedented detail. The measurements revealed something remarkable. The evolving quantum surface followed the exact scaling behavior predicted by the KPZ theory in 2 dimensions. This result is scientifically profound because earlier experiments had only managed to confirm KPZ behavior in one-dimensional systems, where growth occurs along a line. Extending the theory into 2 dimensions dramatically increases the complexity. In 2-dimensional systems, fluctuations interact in far more intricate ways, making experimental verification vastly more difficult. For years, physicists were uncertain whether the predicted universal behavior would survive under realistic laboratory conditions. The new experiment now provides the strongest evidence yet that KPZ universality truly governs a broad class of non-equilibrium systems, even in higher dimensions. Achieving this required extraordinary precision in materials engineering. The researchers constructed a sophisticated layered semiconductor structure containing highly reflective mirrors above and below a central quantum layer. These mirrors trapped photons inside the system long enough for them to strongly couple with excitons and generate polaritons. The material itself had to be fabricated atom by atom using molecular beam epitaxy under ultra-high vacuum conditions. Even microscopic imperfections could have disrupted the delicate quantum dynamics. The laser excitation also had to be controlled with micrometer scale accuracy to maintain the required conditions for the experiment. Beyond solving a 40-year-old theoretical puzzle, the work has much broader implications for physics and future technologies. Non-equilibrium systems are everywhere in nature, from biological growth to turbulence, climate dynamics, and quantum materials. Understanding the universal laws governing such systems could eventually help scientists design new materials, improve quantum technologies, and better understand how order emerges from apparent randomness. The experiment also demonstrates how advances in quantum control now allow physicists to investigate phenomena that were once considered experimentally inaccessible. Perhaps most importantly, the discovery reinforces one of the deepest ideas in modern science. Beneath the immense complexity of the universe, entirely different systems can obey the same fundamental mathematical principles. A growing crystal, a spreading bacterial colony, and a rapidly evolving quantum fluid may appear unrelated, yet they can all follow the same hidden rules. After nearly 4 decades, physicists have now confirmed that this remarkable universality extends into 2 dimensions, bringing one of statistical physics' greatest predictions firmly into the realm of experimental reality.